Thanks for coming to the, what is now Cocoaheads HelsinkiOS mashup. So that just means anything iOS, anything Cocoa, Objective-C, any of those kind of technologies related goes. I want to thank very much Michael Karppinen and company for hosting us today. It's been previously organising the Cocoaheads meetups, which I guess some of you have been to, but I was aware of before I started HelsinkiOS, so it's really great that we could kind of mix those two things together, because it's the same thing, really. So we're going to have a few speakers. Well, I guess 4 people have volunteered to talk today, but the idea today was to make them kind of a bit short. We'll have a little bit, 5-minute break in between if you want to have a chat or whatever, and discuss more of whatever the topic was. And after that, we can then adjourn to the part 4, whatever people feel like doing. So, our first speaker today is Mr. Rasmus Sten, who is going to talk something about DTrace. Welcome.
Thank you.
Thanks.
What DTrace is. How many of you have ever used it? It's about the same. It's nice. Okay, this is actually very introductory, because I figured most people wouldn't actually have used DTrace. So, and most of the talk will just be me showing running and writing DTrace code in a terminal. But I'll first have a couple of slides just explaining what it is. Right. Okay. So basically the Wikipedia explanation is obligatory. It's a comprehensive dynamic tracing framework for troubleshooting kernel and application problems on production systems in real time. But I think what's important to notice is that it's something that enables programmatic tracing of both user space and kernel code. We'll only look at user space now. So basically you write scripts and code to monitor code. And it's made possible by probes that you insert in strategic locations around the system. When they're inactive, they are just NOPs, so they don't do anything, they have no performance impact. And thanks to that, it can always be there. It's installed by default on all macOS 10 systems, and no developer tools needed. So, yeah, you write scripts in a language called D, which is not related to the actual language called D, which I guess there might be a few of them, but the DTrace language D is a subset of C, and a bit limited. We'll get to that later. And a typical example is function entry and return in system calls and libc calls. They all those calls in OS 10 are instrumented with DTrace probes, so you can get right in there, execute code at function entry or function exit, and you get access to the entire user space memory area, and you can even in a destructive mode, which is a special flag you have to use because it's easy to break things, you can actually write to arbitrary memory locations. So that's kind of what it is. It was invented by Sun in 2005, adopted by Apple with Leopard in 10.5. It was made open source in 2005, maybe. It was in Open Solaris. Nowadays, it's not open source anymore since Oracle took over Solaris development, and yeah, so the future of DTrace is a little bit uncertain, or well, now Apple effectively has its own fork, so there is no official upstream, except maybe OpenIndia. Never mind. I'll go right into a simple example. Basically, when you compile something with the default compiler, with the debug option or debug flag, it will go ahead and insert DTrace probes for you, for all your function calls. So if you have like a very simple C program here, let's see if I can actually see what it says. So this is a simple C program that does one local function call, this get username, and in turn that does a system call get end. And if I use a very simple dtrace script, it looks like that. I'll explain the details later. And then run it, I'll get that output. And what we can see, it's maybe hard to see, but you'll just see the start probe, which is, well, the application start, the main function entry, and the get username entry. So that's basically all the function calls that happen inside this process. So the actual dtrace script, it looked like this. So it's made out of, what is it, 5 parts in the descriptor. So this is what describes the actual probe. So it has a provider module function and a probe name, and this is the actual D program. And you'll see that it's empty now, but it's still printed output. And this is why. Or I'll get to that in a few seconds. So basically, the first part of that was the string PID and the process ID, which signifies that you're using the PID provider for that particular process. There's a PID provider for every running process in the system. And the rest of it is dependent on the provider, but in this case, the executable name is the next part, called the module. If I would have used the Objective-C provider, it would have been the Objective-C class name. Function is the function called, and then the probe name is, for example, entry or exit. And here it explains that, yeah, if you have an empty dtrace program, it will always print out some default information about this probe file. So basically you can do a lot by just inserting empty probes everywhere. So a little bit about the PID and Objective-C providers, which are the most interesting when you're debugging regular applications. So basically they provide probe for one specific system process, and you can either launch the process using dtrace, in which case it will set a global variable called $target that you can use in the provider name, or you can browse any arbitrary running process. And so the PID provider, it provides probes into the system libraries and user libraries that have debug symbols, basically. And Objective-C provides probes into all Objective-C classes. So for example, every method, Objective-C method has a dtrace probe. So now I'll actually go straight to showing what this is all about. Oh, sorry. I'm going to need my notes for this because I won't remember what to do. Right. Thought it was mirroring. Okay. Is it possible to see what's going on here?
Yeah.
Yeah, okay. Excellent. So, I'll start out by a very simple example. I have a little program here called Hello World. It takes one argument, which is a integer. It will tell me my username, it will parse the integer, and then it will use the connect syscall to connect to a network host. And it now says that it returned -1 because I don't have an internet connection. So I'm gonna do a very extensive tracing of this by enabling all entry probes in the PID provider. Target. And you'll see here, I leave all these empty. That means I could just as well have write like this, and then it becomes a bit more obvious that these are wildcard entries. They will match any module and any function. Okay. I should also do it like this. And now you'll see that this has now run the program, and it has traced pretty much everything that ever happens when you run a program. And you can, for example, you'll see a lot of these Mac O-loading things. You can see how it resolves dynamic libraries. How, when you call a dynamic library function, it will go to the dilD stub, and then it will do a lazy bind and locate the binary, load it into memory, and all that is now traced. And then you can see some more regular functions like strlen and yeah, you can. This is obviously way too much to make any sense of, but you can get an idea of exactly how much information you can get out of a program. So next I'll show you the third interesting provider that DTrace provides is the syscall provider, which provides you probing opportunities into every system call. So system calls, for those who don't know, are the basically boundaries between user space and kernel space, where you ask the kernel to do something for you. Connect to the network, open a file, or anything like that. So now I'm actually going to write a little bit of D code, and you'll see that I'm using printf. It has exactly the same syntax as in C. I don't have to finish up with a semicolon if that's the only statement I'm going to use. And I'm using a built-in variable here called execname, which is the name of the executable. If I do this now, it will actually show me all system calls that appear on the entire system. So this will mostly show me terminal and dtrace stuff, which isn't so useful, of course, because the terminal and dtrace are working pretty hard now and nothing else is happening. So to make it a bit more interesting, I'm going to show the next dtrace feature, which is predicates, and that's this part. Here you can set conditionals for when your probe should fire, and I use that in this case to exclude stuff like the doc and dtrace and terminal. So now I'll run this script, see how it looks. Yeah, now you can see a lot of other processes here doing. It's mostly open, reads, write, the basic Unix syscalls that you see everywhere. Yeah. So, but this still gets very messy. It's very hard to keep track of all that information. And DTrace is providing a lot of tools for aggregating information. Even so that it has a native data type called aggregations, which I'll show. Let's see if I can find this. I have an Objective-C program here that I've written. If I run it like this, oh yeah, I don't have an internet connection. Is there a Wi-Fi here?
Yeah, it's currency guest.
All right.
It's
I'll go and type it because we have video.
Oh yeah, there's a recorder. You can also change it after.
I can turn off the video if it's okay.
It's too late. Yeah. So I have this little command line program that I've written in Objective-C so that I can demonstrate some Objective-C stuff. What it does is will connect to the Helsinki city servers and download a list of all public toilets. For various reasons, that's what it does. It also has a flag called quiet, which means that it does that and doesn't say anything about it. It's very useful. So I'm going to use that to show you a dtrace aggregations feature. So I'm going to write a pretty long thing here using the Objective-C probe, which has the same format as the feed probe. So when you specify Objective-C $target, and then I'll probe all the init methods in Objective-C. So basically we'll see all objects that are created. And then I'll create an aggregation in here. Basically, you specify an aggregation by using an @ sign and then an optional name, but I'm going to exclude the name now because if you don't use a name, you will use the default aggregation and it will be automatically printed when the probe exits, or the dtrace thing exits. And then as these aggregations, they are subscripted like arrays or associative arrays. And so you can put a string here. In this case, I'll use the probe mode, which is the variable that always corresponds to the module for the probe that just fired. And then I'll call a function called count every time that's called. count is also a special function that DTrace can use to, well, it's used to increment a value in an aggregator every time a probe fires. So when I do this, it will give me a list of all classes that have been instantiated in this Objective-C program, and a count of how often each class has been instantiated. So here we can see that, for example, it has done 51 NSURL connection objects. For example, NSURL connection is interesting because it does the network traffic. So if we're interested in only that, we can specify the class name here, NSURL connection, and see what methods in NSURL. Oh, except that's not what I meant. Then I want to see the function name for all NSURL connection messages. And you will see that the only function that's actually called is init with request delegate. If we want to get more information about what is exactly calling that, we can have dtrace print as a user stack trace for each of these. So I'll just replace that aggregation with the function useStack. And then I'll pop it to less because it's going to be a lot of information. So here we can actually, for every call to NSURL connection init with request delegate, we can see the exact stack trace of how it's called. And we can actually see here that it won't start with my main function because these are printed out of order when you have things that might execute in several threads, like, yeah, or just on a different core on the CPU. If we scroll down a little bit, with most likely, yeah, here is the first column here is the CPU number that it executed on. So here the first main thread started on core number 1, and most of the run loop ran on core number 0. Yeah. So what else? Yeah, but that's all good and well. One more interesting thing is that you can pass information between dtrace probe. You can save variables and store them on a per thread basis or a global basis. And as an example, I have a script here that somewhere there. This is actually 2 dtrace probes, and it uses a few more interesting dtrace functions. One is it uses a C preprocessor, and so that you can define what's called constants, and you can use a pragma macro to enable and disable dtrace options. But basically here we have 2 probes. One that fires on the syscall open, and it saves the path to the file that is open, and then it in the return of the open function it uses that path name to print out whether the open was successful for each file or not, because at the return you don't actually have access to the arguments on the functions to the function, so you have to capture them on function entry. So if I run that, oh yeah, now I have to use that parameter to actually enable the C preprocessor. Oh yeah, I have defined here that we're only interested in Safari. So let's go ahead and start Safari and see if we can get any information out of this. So here we see all file opens that Safari attempts, and we can also see if they succeed and which file handle they use. You can later use that, for example, to save, if you're watching for a particular file, you can save the file descriptor number for that open, and then later use that to capture read calls from only that files or from that file handle. So another interesting thing is maybe network monitoring. So yeah, I should maybe show. So, this is it readable at all? Well, this is a bit more complicated. It introduces yet new features. It has a begin section, which is familiar for people who have used awk and similar things. So this is a clause that is executed before anything else. Then it has a bunch of probes that are all connect entry probes. So you can have several probe for the exact same location. Because in DTrace you actually don't have conditionals, so you can't make if statements or switch statements or anything like that. Instead you can chain different DTrace probes, so you'll set up some variables in the first probe, and then in the next probe you'll set up like this, and just say that, okay, I'm only interested if this variable is this, and here it sets up even further, more variables, and then in the return of the connect call here, it can then print a summary of all this. So what this now does is oh yeah, this was something I added just before this, so that I would remember to mention it. Yeah, so this will actually show us each PID and process name and the IP import they connect to, and also the latency of the connect. Since we're probing both the entry and return of the connect function code, we can actually see how long time it took for the SYN packet to be sent until the TCP connection was fully established. So if I actually reload the web page, well, maybe not that, but let's reload Ars Technica. You see a lot of web process traffic going on there. Not so interesting, but it shows that you can gather a lot of information and summarize it quite easily. And to get it, if you want to get an overview over what a system is doing network-wise, it's kind of useful to use this kind of technique in combination with aggregation. I have another script here. It basically does the same thing, but in the end, instead of printing out the table, it stores everything in aggregation with two keys, the executable name and the address it connects to. So if I run that script, reload some web page to trigger some traffic. It would be fun to get some other traffic than Safari also. That's SSH somewhere. Okay, and now when I exit this, it should print a summary of this. And it didn't catch the SSH for some strange reason. Well, that's a demo effect, I guess. Basically, this now gives a table of all the IP addresses that each process has connected to and how many times it has connected to this, so you can get an overview over what network traffic your system is responsible for.
So chaining that with write or read calls, I could maybe get the byte counts also for
Yeah,
the
definitely.
connections?
Yes.
So that's something I've been wanting
Yeah.
to have an app that shows me which process is sending how many bytes or receiving how many bytes from which address.
There's another provider also that I didn't mention called the tick provider. It gives you the option to periodically fire probes. And that way you can actually keep counters on like how fast or how the bandwidth of a particular process of a particular TCP connection, for example. So you can do a lot of things like that. That was actually all the examples that I had. I'm just going to mention a little bit more about. Yeah, well, I took away the examples that I had because they aren't suitable for public consumption. But there is a way. You can write to random locations in memory. So if you're, for example, trying to trigger bugs in a program, you can fool it into opening a different file that it already opened, or that it thinks that it opens. There are some limits because you can, for example, allocate new memory. You have to use whatever allocated memory already exists in the user space process. So if there is a file name buffer, then you better keep within the existing length of the path. But of course, you can always figure out those limits, and if you're creative, you can create quite big buffers. But you have some other limitations also in DTrace. The programming language, it has no functions, no branching, no loops, so you'll have to do tricks like shading of probes and things like that. And you have a very limited amount of memory for your own variables. You have about 256 bytes for strings. After that, it starts to discard stuff. So you have to be very conservative about using global variables. And the most frustrating limitation is perhaps that paged out memory can't be accessed. So especially if a function entry uses a pointer to something, you can't access that memory if that memory hasn't been used in a long time. Quite often it's in a page file somewhere, and you can't read it because you can't do anything that blocks basically inside DTrace. What you can do is often to save that pointer and return to it at the return probe for the same function, because then quite often it's been accessed by the user process, so it's been paged into memory and you can read it. But there is no way of catching this situation. You'll just get a generic error that this is invalid memory. So you'll just have to try to figure out ways around it and always use memory when it's also used by the program. Yeah, I think that was all I had. This is a very big topic, and like I could just go on and on, but I thought I would just give a very brief introduction, because for many people DTrace is something you hear about and you think that that seems very useful, but you never take the step to actually learn just a few basic DTrace commands that it gets you going very quickly. But there is a very good book called DTrace Dynamic Tracing on Oracle Solaris Mac OS X and FreeBSD by Greg and Morrow, and it's very short and to the point, and you won't have lost so much time reading it, and it has a lot of useful examples, and it treats all platforms equally, so it has quite a lot of Mac OS X stuff also. Then you have stuff like the DTrace toolkit, which contains an immense amount of DTrace code. Oh, and any Mac OS X installation has a bunch of DTrace script pre-installed also. You have some scripts like file by proc.d that lists all file accesses by process, and new proc.d that lists all new processes created with arguments. All those scripts are very useful to learn and experiment with DTrace.
Are they installed with the operating system, or
Yeah.
not with the dev?
Yeah, no, they are. As far as I'm pretty sure they are they come with the default DTrace package, basically. And then there's an old article on mactech.com that explores the Mac OS X specific DTrace things, like Objective-C probes that naturally don't exist on any other platform. Okay, that's it for me. Any more questions?
I could make a comment about the DTrace app. Since 10.7, I think you could use nettop command to do something like that. So DTrace is awesome, but there's also like an app for that, a command for that.
It's quite often I end up writing 100 lines of DTrace code, and then I Google the program and figure out that someone has written an app for it.
Yeah.
It's slightly annoying, but I learn something in the process.
Have you tried attaching or running DTrace in the? Can you run it in the simulator? Can.
Yeah,
Right, the
yeah,
iOS
yes,
simulator.
you can attach like an iOS app in the simulator. It's basically a regular user space process. So you can trace an iOS app running there also.
So it's trivial to do it from the command line. Like
Yeah. I knew that question would come, so I just tried it the day before yesterday just to make sure I could answer it. So yes, it works, and it has all the regular probes as far as I could see. You can trace all the Objective-C classes and stuff like that.
Can you do it remotely on the iOS device?
No, you can't do it on a device.
Okay.
You're only on the local process,
Maybe
as far as I know at least.
Yeah.
One question, you mentioned that that program needs to be compiled specially for DTrace. So if you take a program that is compiled with DTrace and one that is not compiled with DTrace, what's the difference? I mean, is it like debug symbols, or what's the...
Yeah, so if you want to trace local function calls within that program, basically, then you need to have it compiled with debug symbols. As soon as it makes dynamic library calls outside that very executable, then you can trace it anyway, because naturally that program needs to know the symbol that it's looking for, and you can trace it. But if that function has, or that program has a function internally, that won't be visible to DTrace unless you have debug symbol.
Okay, thanks very much.
take a couple of minutes while I figure out who's talking next.